Hi everyone, I'm Tianchen Xie from UC Berkeley, and I'm going to present Updatable Private Set Intersection. This is a joint work with Sai, Pei Han, and this work is done by internship at Visa Research. First, we need to define the private set intersection, and that Alice has set X and Y, Bob has set Y, and they are going to compute the intersection of X and Y, and without any other information is leaked. There are several applications such as private contact discovery or private contact tracing. And we're going to focus on a private contact tracing scenario because it fits the updatable setting. On day one, we got several cases represented by these four bins, and we got some client who is get some contact. And in day two, we got several new cases and more contact by the user. And the scale of the data is like following. A user may meet 10 or hundreds of people per day, and he got thousands of friends maybe in total. And for the client, we got 400 kilo new cases per day and 500 mega in total. A naive solution would incur quasi-linear computation and quasi-linear and a linear communication per user per query. So it means that for each query of contact tracing, it needs to download hundreds of megabytes from the user from the server. Our target is to reduce both computation and communication, and it will be sublinear to the existing set and quasi-linear to the new set. In our work, we divide into the two different variants: two-sided updatable PSI based on DDH and one-sided updatable PSI. The two-sided version will reveal the intersection to the server and the client both. And one-sided is more private. It will only reveal to the client. There are several existing works such as DDH-based, OT-based, circuit-based, and for the two-sided version, we are going to focus on the DDH-based solution. First, we need to define the privacy definition of the updatable setting. Alice and Bob already get A0 and B0, and they already get the intersection of A0, B0. Let's assume that. And for a new set, A1 and B1, they're going to compute this A set intersect with B set and nothing else. So this is our privacy definition, and we can exploit a little bit. So Alice will additionally know A0 intersection with B1. That's a contribution of her old set. And she will also know A1 intersection with B because that's a contribution of her new set. And similarly for Bob. So based on this observation, we can have a construction. So let's assume Alice got key 0 and Bob got K1. That's DDH key. In the first message, Alice is going to send a new raised to K0. And Bob can raise it to K1 again. So he know a new raised to K0 times K1. So he can compare with this old set, and he now know a new intersects with B old. And similarly, Alice will know the A old intersects with B new. Now, Alice wants to learn the A new intersection with the whole B set. Naively, she can run this separate PSI on A new and the whole B set, but this will incur linear communication to the size of B. We will not accept that, but we have an observation here. Bob already know A new intersection with B set, B old, so he can replace the B old set with this A new intersection with B old. That it will not change the result because it's intersecting with B new. It is intersecting with A new. So this new set here will be the size of this new set will be the size of A new plus size of B new at most. So this new PSI, new separate PSI, will only incur linear to the A new plus B new size. Now, let's learn this A new intersection with B set. And similarly, and Bob will learn B new intersection with A set, and they are done. So they can combine these two results and get the new intersection. consider one-sided PSI where Alice is the client and Bob is the server. Now Bob learns too much additional information in the previous protocol. So we are going to adopt a new protocol. It's a data oblivious based on a data oblivious data structure. And for each entry in this data structure is going to be a badge of size sigma. And each tree node has capacity of 4 sigma. So each tree node has node sigma and the capacity of 4 sigma. And why is it 4 sigma? Because we want to avoid overflow in case that the random distribution is not good enough. And each element will be encrypted by Bob's secret key using this additive homomorphic encryption. Here, gray node means that it's filled with sigma, expected sigma elements, and blank node means that there's no data. So, assuming that this picture is a BO set, represent a BO set, and here comes a B new of size sigma. And now the Bob will try to push it into the root node, and if it's already occupied data, we will employ a split function to evenly split data into left and right child. And now root node is empty, but left and right child is also occupied. So it recursively split again until it hits the empty level. And here is level 3. Level 3 is empty. And now he filled data to the level 3 and stop the recursing. So now the question is how to define split. It's actually quite easy because split is, the purpose of split is randomly throw element into left and right child. So we can define a random hash function, hx, map element x to a 0, 1 string, and x is a ciphertext, it's a plaintext. And for hx at level I, we are going to throw it into the left child if the random hx is indicating 0. Otherwise, it will be thrown into the right child. And in expectation, each bin is going to load sigma elements. And here, the capacity of each bin is 4 sigma, so it will not overflow except for negligible probability. Now consider a query. Alice has a new here, and consider element AI. If the hash is 0, 1, 1, 0, we can trace through from the root to the leaf. 0 left, 1, 1, 0. Okay, so there are log different bins. And if AI is actually in the B set, the AI must be in one of these bins. So Alice connected all the bins, and she tried to randomize these bins by applying a mask. So she computed mask bin plus AI bin plus alpha minus AI using her secret key, using server's secret key. And she compute the encryption of alpha using her own secret key. And notice that if the green guy contains AI, it will cancel each other and only alpha is left. So upon receiving this mask, the server will immediately decrypt and get beta equal to this thing, and it will not leak any information because alpha is randomized for each element. And the server also randomly sample gamma and compute alpha minus beta on the ciphertext. So the server will never know the result of alpha minus beta, and he masked this result by gamma. So notice that if green contains AI, then alpha minus beta should be 0, and gamma is not relevant here. And the server send the whole thing back to the client. Client will decrypt this thing and see if it's a 0. If it is a 0, then AI is in the intersection. So the client can apply this technique to every single AI, and she can get the result A new intersects with B. How about the AO intersection with B new? We can use the DDH again, assuming that the client maintaining AO raised to K0, K1, and as the B new comes in, the server can raise it to K1 and send to the client. Client can raise to K0 again and get the intersection. That's all of our protocol. Any question is appreciated.